Yeah, my grandpa was pretty cool. I think the thing about him that I would want to put out there into the listening audience is that he was like so ridiculously optimistic about everything all the time. Even though he was an orphan, even though he had polio and was partially paralyzed for his whole life, even though he lived through World War II, he always saw the good in people and he always thought there was something that he could do to help. And he did help.
Hello, everyone, and welcome back to In Plain English, the podcast that is all about making science approachable, open source, and jargon-free. I am your host, Jamie Malfa, and today I am joined by my wonderful friend, Sharon Abada. Sharon, welcome to the podcast.
Hello, thank you for having me.
Can you give a brief introduction of yourself?
Sure thing. So my name is Sharon. I am a fellow in rheumatology at UCSF in San Francisco, meaning I've completed medical school at WashU with my dear Jamie, and went on to do my internal medicine residency here at UCSF and then stayed to do some extra training in rheumatology.
Awesome. And yeah, I have you on today because a couple months ago now, you gave a talk that I attended virtually that was a really cool kind of blending of your own family history and the history of a life-saving medical advance that is actually pretty common. And actually, some of our listeners may have had this when they were infants or may have children that received this treatment. But it was a pretty incredible advancement that really improved, really reduced infant mortality, especially for preterm infants. So I thought it was a fantastic story, and I'd love for you to tell our listeners about it.
Sure thing. So I've known vaguely that my grandfather was involved in the discovery of pulmonary surfactant and what its clinical indications and implications were. For my whole life, it was something that people would sometimes bring up, at the dinner table on Thanksgiving or something like that. To me, my grandpa was always a very optimistic older gentleman with dementia who, needed a lot of support and help. And so I never really met him in his heyday when he was a young fellow himself like I am now, or later when he was chair of pediatrics in a couple of different places, including at Oakland Children's at UCSF. So this was kind of a story that I had vaguely known. My grandpa was involved in something big, and then I never really looked into it. And because he was older and didn't really talk about it in that much detail, I never knew. So then when I was tasked with coming up with a topic of my choice to do some deep research on, I thought this would be interesting. And moreover, it's something that happened at UCSF, where I now spend the vast majority of my waking hours. So I felt like it was a good opportunity to explore both that family history. What did my grandpa actually do? And then also, how did this surfactant discovery come to be?
Yeah, for sure. Can you first kind of give a brief overview of what surfactant is? Like, why is this discovery so important?
Right. Absolutely. So I think before we talk about surfactant, we need to talk about the structure and function of the human lung and, of lungs in general. Lungs are essentially kind of like massive internal trees with branching trunks, meaning like your trachea branches into bronchi, branches into bronchioles. And at the ends of these tiny little airways are these sacs called alveoli. Those are sort of like the leaves on the tree. You can imagine a ton of little bubbles on the end of various branches of airways. And that allows for the lung to have a huge surface area for gas exchange. That's the main purpose. Now, if you think about a balloon, for example, that when you blow up a balloon with air, the thing the balloon wants to do is collapse back down. There's a resistance to staying inflated. That same thing happens in the alveoli. When you inflate your lungs, there's a huge resistance to the alveoli staying open. Those little bubbles, they all want to collapse. That's actually because there's a tiny layer of water or of fluid at the alveolar interface with the air that provides like a ton of surface tension. That surface tension draws each of those bubbles in to close. So that's a problem, right? And if you actually look at the lungs and you think like, wow, how do they even work? How do these little tiny bubbles even stay open if there's a little bit of fluid there? That was something that actually caught physicists' attention because they looked at lungs, they did the calculations, and they said, if lungs had the surface tension, if the alveolar surface had the surface tension that we think it should, the lungs should not stay open. Like everyone should basically be suffocating all the time. So there has to be something there that's reducing the surface tension in each of these tiny little alveoli. And that was actually where the discovery that there might be low surface tension came from. It was like a physics problem, which is pretty amazing.
Yeah, physicists, you don't really think of them as like doing biology that often.
Right. And the first person to actually recognize this as a problem was a German gentleman in 1929 named Kurt von Niergaard. He did some calculations and was like, there's got to be something in these alveoli, and he called it a surface active substance that is preventing them from collapsing. And later, it was discovered that there is in fact a substance called surfactant that's largely made out of phospholipids. And those phospholipids all line up on the alveolar surface, and they basically break up the intermolecular forces between the fluid molecules and allow for decreased surface tension in the lungs. It keeps the alveoli open that allows people to breathe.
Cool.
So surfactant molecules, there are many different things in surfactant. So like any biological substance, it's of course not simple. But the main components are these phospholipids, which have hydrophilic heads and hydrophobic tails. And so they're like sort of what would make up the bilayer of a cell membrane that we think of, except it's just a monolayer. They line up along the alveolar surface and they go like, we're going to keep this alveolus open. And it's largely because of those hydrophobic tails that they're able to do that.
Cool. Yeah. So very important for breathing.
Yeah. We like breathing in general.
Yes.
I mean, I like it. That was how surfactant sort of came to be discovered, was because people realized that there had to be something there performing that function. But then, the properties of surfactant and its clinical implications really took quite a little bit of work to elucidate. If you think about it, basically people in the 1950s who started doing this research, which is the focus of the story that I'm telling, they didn't know about Kurt von Niergaard's research at all from the 20s because it was written in German and, probably printed on some piece of paper somewhere, and there was no internet.
Right. Got lost. There was a whole war.
There was a whole, couple of things happened between 1929 and 1950. So anyway, we come now to the late 1940s, actually, and during World War II, pulmonary research had something of an explosion. The reason being that a lot of toxic gases got used during World War II. And also, there was a lot of emphasis put on researching cardiovascular health, so to speak, in the sense that, like, how do our soldiers survive really dramatic conditions? How far can they run? How fast can they breathe? All these sorts of things. And so the person who I spent a lot of time researching and reading articles by was a gentleman named John Clements. He was born in upstate New York in 1923 and did his MD at Cornell in the 40s, actually on an accelerated track because they needed people to do research and they needed people to leave medical school, essentially to work for the Army. So he was drafted to the U.S. Army Medical Corps in the 1940s and stayed on as a civilian employee for about 10 years after that because he really enjoyed it. And essentially he was like told to be a pulmonologist and told that he was going to study lungs because that's what the Army needed. So he studied toxic gases, he studied lung function, and he came to the same conclusion that von Niergaard did, which is there has to be something on the surface of these alveoli keeping them open, otherwise the physics just don't work. So he developed a really interesting technique to study this substance. It sounds crude today, but it was really pretty genius. He essentially took lungs from animals, ground them up in a blender, and then extracted whatever fluid he could from that ground up,
lung
delicious
smoothie.
material. Lung smoothie. Yep. So he took the lung smoothie and he placed it on this balance called a Wilhelmy balance. It's essentially a table where you put a bunch of fluid in it. You put the surface active fluid that you want to test. And then there's this bar that moves across the table to compress and expand that fluid to test the surface tension properties. So what he discovered was that not only does the surface tension go significantly down with the introduction of this fluid, but that it actually also behaves differently when you compress and expand it in a way that mimics lung compliance. A lot of the things that we observe about lung compliance that we, might attribute to the internal elastic properties of the lung may also be related to surfactant.
Huh. Made a lung on a little tilting board.
He made a lung on a tilty board, right? So he made a lung smoothie and then he made a lung on a tilty board. And in that, he was able to ascertain that this is a complex fluid with complex mechanics. Right. He was just doing this because he liked math and science, as far as I can tell. There was no clinical application discovered until 1959, actually, when a woman named Mary Ellen Avery, who was working in a lab at Harvard, learned how to use John Clements' Wilhelmy balance and then tested the lungs of premature infants and other infants who had passed away. So sort of, it sounds very sad, and it is.
Yeah.
But she made lung smoothies out of the infant lungs. And then, she graphed which infants were born prematurely, which infants were not, which infants had respiratory distress symptoms, which infants didn't, and tested the surface tension of each of their lungs, was able to ascertain that it was the infants who died of respiratory distress syndrome who seemed to have very high lung surface tension. And it was premature infants who were more likely to meet that description. So she was the one who said, listen, this surfactant stuff seems very, very related to neonatal respiratory distress syndrome, which is the main killer of premature babies.
Right. And a lot of babies died prematurely before we discovered this stuff.
So now in the modern era, we think of 22 or 23 weeks of gestation being kind of the lower limit of viability. And that lower limit is being pushed lower and lower all the time by medical science. At this time period, 34 weeks could be considered a death sentence.
Which is, I don't know, that seems really crazy to me. So my partner is a nurse in the children's cardiac ICU. So not exactly the NICU, but they do see a lot of kids that were born prematurely. Sometimes they're floated to the neonatal ICU. And a 34-week-old baby now would be like big, pretty healthy, like not having a whole ton of problems.
Right. There is absolutely no world in which 34 weeks, purely because of prematurity, is considered a viability issue in our modern day.
Yeah.
So that, the 1950s, 1960s weren't that long ago. So it's really amazing. And the tools that people were using to do this were all mechanical. It was all hand calculations written on paper. I poured through my grandpa's old notes on this topic, and they were all just sharing articles with each other, talking, collaborating. It was a really pretty remarkable, piece of work. And, I thought that Mary Ellen Avery's involvement was really critical here, that a woman who had gotten an MD in an era when women really didn't go to medical school discovered this absolutely phenomenal discovery. And that the men around her, who maybe had a slightly easier time getting where they had gotten, were really quite supportive of her and supportive of that being her discovery. I thought that was also a really nice touch in this story.
Yeah. Yeah, I feel like a lot of times when you hear about the famous women of science, it's oftentimes about their struggles. And I'm sure that she faced a lot of struggles and how not accepted they were by the medical community or the scientific community. But it's really nice to hear that she was actually supported in this.
She really was. And she went on to have a tremendous career of her own, primarily at Harvard, and got, I think, a presidential medal of some sort. Really
nice.
Yeah, we like those. So that's sort of the early discoveries. Basically, we went from von Neergaard, this German guy, being like, hey, the lungs seem to have a surface active thing, to that being essentially rediscovered in the 50s by American and British scientists doing World War II research, to this female physician at Harvard doing her research fellowship, finally making the clinical connection that really caused this field to blow up. Mm-hmm. Because you can imagine, once we have that clinical application, money, people.
The funding, yeah.
The funding, yeah. And so that's really where my grandpa comes into the story. He had grown up in Cleveland, and his father was a physician, but both of his parents died when he was really young. And I think he always wanted to go into medicine like his dad. He didn't have any particular trajectory in that other than just being quite ambitious, as far as I can tell. And he went to medical school at Case Western Reserve University in Cleveland, where he was born, and got polio when he was in medical school. We don't think about getting polio anymore. That's another difference.
It really was a different time.
It really was a different time. The fun fact about Mary Ellen Avery, just to go back for a moment, is that the reason she got interested in lung research was because she got tuberculosis during her residency.
Oh my God. That's wild. Yeah. Now we just get our little TB test when we go into med school and make sure that we're all vaccinated. Like, that doesn't happen anymore.
It actually does quite a lot in certain areas of the U.S., which I've learned since being in medical residency. Yeah, tuberculosis is still an issue. Polio is less of an issue.
Right. We've kind of figured that one out a little bit more. Get your kids vaccinated, please.
Please vaccinate your children. Okay. So, yes, he gets polio in medical school, and he can't use the right side of his body properly. And then, he's wondering, how do I be a doctor if I can't lift things? And he ultimately determines that he can't lift an adult patient, but he could still lift a baby. And so he goes into pediatrics.
That's one way to go about choosing a specialty.
Yeah, I was like, that makes sense. And he rolled with it. And then he became obsessed with babies. And that's all I heard about my whole childhood from him. Babies this, babies that. I'm like, seriously. But he became a neonatal pulmonologist. Essentially, after finishing his pediatrics residency, he worked in private practice for a while and then decided that he needed to do research. So that's how he ended up at UCSF. John Clements essentially got recruited to UCSF as well a year or two before my grandpa came as a fellow. And then along with a couple other fellows, my grandpa worked in John Clements's lab. John Clements, as you'll remember, is the gentleman who did the lung smoothie, lung on a table experiment before. And so they essentially continued their experiments, but this time with improved technique. So rather than make a lung smoothie, they would take beef lungs, which are, available at slaughterhouses. They would squirt saline down into the beef lungs and essentially do a washing of the lung fluid, like a lavage. And then they would take that lung fluid that they got out of the beef lungs, and then they would run it through various chromatography methods to try to separate out the different components, and then test which components of the fluid were the ones that actually had the property of reducing surface tension. So my grandpa was essentially the one who wrote the paper that said phospholipids are the active component of surfactant, which is pretty cool. Yeah, I'll take that.
That's pretty awesome. Win. Yeah. He's like, he identified this one. This is the one.
Yep. It's the phospholipid fraction that makes the difference. The fun fact that I'll tell you about this story is when I interviewed some of my family members about my grandpa's involvement in this project, I specifically asked my oldest aunt some questions because she was the only one who was old enough in the family to remember living around UCSF at this time.
Yeah.
And without prompting, without even bringing up this whole cow lung experiment, she has a very distinctive memory from childhood of my grandpa coming home from the slaughterhouse because he, as the fellow, was sent to do the grunt work of actually picking up the cow lungs from the slaughterhouse. And she just remembers that his ears were all white and he was kind of shaky because he really hated it.
Yeah, that doesn't sound like... It's one of the less pleasant aspects of research.
Right.
Sometimes very messy. Involves interacting with things we'd rather not think about.
Well, and, I think there's two things to think about here. One is we do a lot of modern day animal research on animals that are still alive. And that's really important research. And our modern medical scientific world would not work without that kind of research. I think of this being slightly different and maybe a little bit more acceptable in that, these were cows that were already being used for meat and their lungs would otherwise be tossed. And why not use them for medical science? I'm not sure it would pass regulatory standards today.
Yeah, I don't know about that one. I mean, to me, it seems very, efficient to use the entire animal rather than it going to waste. So I'm like, yep, I'm in support. It actually, the thing that this reminded me of is that a lot of people in my department do like human tissue research on like human nervous system tissue. And this is from organ donors, like people who already have agreed to like donate their organs after they pass. And so you get the organ donor into the hospital and the surgeons remove all of the organs that are going to go to people to be like life-saving medical treatment. And then grad students and fellows go in and get the nervous system tissue afterwards.
Yeah, I do have to wonder, though, like with modern day labor laws, whether fellows would actually ever be tasked with going to the slaughterhouse to pick up the cow lungs today. And I have to think that the answer is no. As someone who's doing a modern day fellowship at UCSF, I don't think that would pass the sniff test.
Yeah, no, probably not.
So the research group then went on to do some additional studies to further say, okay, we know it's phospholipids in the surfactant that reduce the surface tension. Now, which phospholipids actually do it? So they fractionated out the phospholipids and determined that it was primarily one phospholipid called dipalmitylphosphatidylcholine, or DPPC. And they also found that surfactant contained a pretty significant protein fraction. Like up to 10% or maybe even higher of the surfactant was actually made out of proteins, which are not phospholipids. They're like a completely different category of molecule, which we'll get back to in a minute. But the logical extension of the discovery of surfactant was, well, if surfactant reduces surface tension and if surfactant is not present in premature babies, if we give surfactant to premature babies, then they should live longer.
That's pretty good logic. Why aren't premature babies making surfactant?
It's a good question. I don't actually know the answer to that.
Okay.
I just know that it isn't produced until about 34 weeks or so, maybe even a little bit later. I have to think it has something to do with the development of the type 2 alveolar cells themselves, or that they have not yet grown the capacity to release surfactant. Because surfactant is a material that is produced in a specific type of alveolar cell called type 2 alveolar cells, which became the next line of research as well. So simultaneously, while thinking, if we administer surfactant to babies, what's going to happen? Researchers were also starting to use electron microscopy to map out surfactants production and trafficking around the cell itself. So that's what people spent a lot of time on over the next decade. But the question of what do we do with this? Now we know that babies don't make this. Now we know that it's really important to prevent development of respiratory distress syndrome and alveolar collapse. So in order to test this theory that administering surfactant to babies might be a treatment for neonatal respiratory distress syndrome, the group of researchers from UCSF actually traveled all the way to Singapore in the early 1960s to administer surfactant to babies over there. The reason they chose Singapore was because it had a high clinical volume. Not sure why there are so many babies in Singapore, but there were more babies over there than there were in the United States. Also not sure, what the regulatory standards would be about, like, randomly going to another country to test.
How did they get permission to
treatment.
Do this?
Man, it was the 60s. It was loosey-goosey, wild and free times.
Just like, yeah, sure, Singapore. Great.
And a lot of laws about human research had not yet been fully established.
That makes sense. There was a lot of stuff that happened in the 60s that made those laws very, very necessary and important.
Yep. And we'll leave it at that. So I think my grandpa went to Singapore as a part of this research group. They administered nebulized surfactant to babies, and it didn't work.
What?
That was the outcome of the trial. It was a negative study. They were all very disheartened, and the researchers had actually concluded that surfactant was not a good treatment for neonatal respiratory distress syndrome, and that maybe surfactant wasn't even the culprit in neonatal respiratory distress syndrome because this didn't work.
Oh my God.
And that it was actually ischemia to the pulmonary tissues.
All of this research is coming apart.
It fell apart, and it set the whole field back about 10 years that they made all these conclusions, and it was published in this very large journal article. So unfortunately, my grandfather left UCSF on kind of a bummer.
Aw.
Because then he went on to go do research elsewhere, completely pivoted in his trajectory, decided that, actually basic science research and translational research was not for him. He would rather be researching mother-infant bonding and developing the idea of a doula, which is what he's really known for.
Well, that's also really cool.
Yeah, and he did really very serious research on how mothers and infants bond, and went on to sort of be someone who was really pushing for skin-to-skin contact in the first few minutes of life and not separating babies and mothers. That was a lot of people at the time, but he was one of those people, and that's considered standard of practice today.
Yeah.
Because we know how important that is. So that was really what he ended up being known for, and why he became so prominent in his field, why he had an obituary published in the New York Times, etc. It wasn't any of the surfactant stuff. This is just the research that he did when he was like the lab munchkin fellow. When you have to do a research project in order to get through your training.
Yeah, but it ended up being super important research.
Right. And the idea came back around in the late 70s and early 80s. The reason that this idea stayed at the front of everybody's minds is because, in 1963, actually one of JFK's children passed away from neonatal respiratory distress syndrome. And so funding sort of poured back into this field at that time. John Clements never gave up on surfactant. He kept studying it.
He believed.
He believed the cellular mechanisms, the microscopy. They were characterizing everything they could about production, movement, and metabolism. Other developments in treating neonatal respiratory distress syndrome happened concurrently, specifically positive pressure ventilation. Positive pressure ventilation and antenatal steroids given to the mother were the two most important. The antenatal steroid story is actually amazing, and I wish I remembered it better. But essentially, there was this guy in New Zealand who was studying sheep and goats and, development and birth and all this stuff. And he gave one of the mama goats, I think, steroids. No, he gave a baby goat steroids. He gave some animal steroids, and he thought the animal was going to die, but then it didn't.
And he extrapolated from this that the steroids might help people survive.
Yeah.
Okay. How do the steroids help the babies breathe?
Right. So the steroids are actually given to the mother.
Okay.
And they're given to any mother who's gone into premature labor at a certain number of weeks. And this is where me not being an OBGYN sort of starts to fall apart.
Corey, we need Corey.
Corey, where's Corey? Corey, for the podcast, is my roommate who's now finishing up his OBGYN residency. It speeds up the production of surfactant in the baby. I don't know that we totally understand how that works.
Huh. Well, so it is a surfactant.
It's still the surfactant. And the positive pressure keeps the alveoli open because it's positive pressure.
Right. That one seems a little bit more like, it's a bit more of a hammer of a solution. They're like, well, if the lungs aren't staying open, we will make them stay open.
And truth be told, that is the main treatment for neonatal respiratory distress syndrome today, is positive pressure ventilation. And that's for a variety of reasons. It's very effective and it's non-invasive are the two main ones. So to go back on the surfactant story, so in the 1960s, we decided that, this is not a good treatment. It didn't work. Administering surfactant is a dud. But in the 80s, someone thought, let's give this another try. And they changed the method of administration. I don't know all the details about how this was decided, to an intratracheal suspension instead of a nebulized treatment. So intratracheal means you have to have the baby intubated, and then you essentially dollop fluid into the endotracheal tube and let the fluid marinate in the lung.
That sounds way more invasive.
Right. So we don't like intubating people if we don't have to intubate people, and babies are included in that. So you can see why, if a baby can get away with just CPAP or BiPAP or some sort of positive pressure, that would be preferable to administering surfactant when the baby has to be intubated.
Right. And just keep the baby alive and breathing until they can start making surfactant on their own with their own little tiny lungs.
Right. So I asked my friend Faith, who's also your friend, Jamie.
Yes.
How has she actually seen surfactant administered, and how does it actually work? Because she's now a neonatology fellow.
Yay!
And she said, so you like put the baby on their side. Well, so the baby's intubated. You put the baby on one side, you administer the surfactant, you let it like sit around in one lung, and then you like put the baby on the other side and then put more surfactant in and like let it wash around the other lung. It's like, I don't know, it's like some sort of funny tilt table.
And you're just like, tilt them one way, tilt them the other way, make sure it's all nice and coated.
Exactly.
That's really funny. I mean, it's not funny, but it's a little funny.
It's a little funny. The repeat research in the 80s was a positive trial, meaning, yes, administering surfactant is actually tremendously effective. And it has made it onto the list of like WHO mandatory medications for developed countries. Like, you must have surfactant on hand, even though it's more of a treatment that's used when things like CPAP don't work.
Right. But it's still like gonna be life-saving when CPAP doesn't work.
And so in terms of those surfactant proteins I was talking about, like, why did I even mention that? It turns out that surfactant proteins are actually really important for the function of surfactant. Some of them deal with immune function of surfactant and fighting infections in the lungs. But some of them also are really critical for the function of surfactant to happen. And I don't want to go into too much detail here, but mutations in surfactant proteins cause essentially neonatal respiratory distress syndrome by default in people who are lacking those surfactant proteins.
So, yeah, so it's those phospholipids, and it's also the proteins, and you kind of need all of them to be working correctly together in order to breathe. I have a question. Where are they getting the surfactant that they give to the babies from? And does it also have the protein in it?
That's a great question. The surfactant that is administered to babies, I'm more familiar with the original formulation, which was called ExoSurf, and that was developed by John Clements, actually did not have any proteins in it. What it did have was a additional substance that I'm blanking on the name of, but it was like a very commonly found lab substance that you just added to the surfactant so that the surfactant could traffic properly to the surface of the alveoli. Sort of performed part of the functions that the proteins would, but it wasn't itself a protein.
But there's a different formulation now.
Yeah, I think most of them are synthetic. They're lab made.
Yeah.
And some of them are bovine derived, I think.
I was going to say, like, are they still getting it from the cows?
They may still be getting it from the cows sometimes.
Interesting. So, like, I guess what brought that up to me was that some of the surfactant proteins also have immune function. And so does it cause inflammation if you give the babies the surfactant that's from the cows?
Right. It's a good question, right? Do people have rejection of bovine surfactant? I think the answer has been no.
Okay.
And fortunately, the substance that John Clements tested as being the additive to the surfactant that he made in the 80s and 90s was also not immunogenic. Like, it didn't cause an immune reaction in the babies. But I think that was also partly a stroke of luck. That's
really good. Yeah, that's good. Because, you know, you could administer all the surfactant you want, but if it causes the lungs to get inflamed, like, you still can't breathe.
Yeah. We'll chalk that up to, like, good fortune and some educated guessing on the part of the researchers.
Yes, we love educated guessing. That's like almost the entirety of research. Educated guessing and getting really randomly lucky.
Educated guessing and getting really randomly lucky, a story of modern medical science.
Yeah, for real.
I mean, it's true.
It's literally how we have penicillin. Someone left their moldy plates out too long.
Yep. So I know that's been a bit of a journey from lung smoothies to baby tilt table administration of surfactant, but it really was a very logical but also multifaceted story. We started with a physics problem. We need something to keep the lungs open. And then you move on to the clinical connection that Mary Ellen Avery made. The research that at first didn't work because turns out the nebulized DPPC is not enough. They really needed that trafficking molecule to actually help the surfactant get where it needed to go. The discovery of surfactant proteins helped them get there, and all the research that was done in the 70s on trafficking mechanisms in the cell. So John Clements developed the first artificial surfactant called ExoSurf. John Clements, I guess we're calling lung smoothie guy.
I'm so sorry for that, by the way.
That's okay. I know it's very memorable to me. He developed ExoSurf. And this guy, I have to tell you, like, having read now so many of his articles and interviews with him, was incredibly endearing. All he cared about was science. Like, he just loved science, and he just wanted to do science all the time. He didn't care about money. He didn't, I think he did care about the clinical implications, but he didn't really care about like becoming famous because of them. So he collaborated with a industry partner to actually make ExoSurf patentable, administrable, sufficiently studied to get FDA approval. And he did all of that with the help of the industry partner, which was called Burroughs Williams. And it was a tremendous success. It was the fourth most lucrative patent in the UC system at the time, or maybe ever.
Wow.
And subsequently, other people have created different surfactant formulations that are used more commonly today. John Clements was nominated for the Nobel Prize many times, but he didn't get it. Aww. He did get the Lasker DeBakey Award, which is maybe like the highest prize that's available in medical science, and actually stayed on as a professor at UCSF well into his 90s, and finally retired and became emeritus at some point in there, and actually passed away a few weeks ago at the age of 101.
Oh my God. I was not, I had assumed that he passed away a long time ago. Like,
no,
he was active doing research in the 50s, which is at this point like 70 years ago.
Right. Yeah.
It's
70
crazy.
Years ago. He was a professor 70 years ago.
Jesus. Well, I mean, I guess this episode is also like in memory of your grandfather and also the lung smoothie guy.
His incredibly famous and successful PI, Dr. John Clements.
Yes.
No, I mean, so when I was doing this project, because it was still last year, I knew he was still alive.
Mm-hmm.
I had really hoped to meet him, but I think he was probably not in quite the right shape to meet anybody.
Right.
But I guess I didn't expect that in doing this project that I would like totally fall in love with this 100-year-old guy. Just like throughout the process of reading his stories and reading the way that he talked about the science, it was so incredibly endearing. I feel like there was a purity of spirit there and of focus that is pretty rare. And I'm not surprised that he was incredible, but he was also very quietly incredible.
Yeah. He sounds like a very wholesome role model. I feel like we need those in science.
We do. So the current chancellor of UCSF is named Dr. Sam Hawgood, and his essentially success story started when he decided to join UCSF from Australia. He moved here because he did an interview with John Clements and decided, I have to work with this guy. Came to UCSF in the 80s, studied in Dr. Clements' lab, did research there, and was actually one of the first clinical fellows to administer surfactant as part of the new trial.
Oh, wow.
It's a huge part of his story. It's the reason he's here at UCSF, and he stayed on and became the chancellor. And when he was talking about John Clements, because I met with him to get his story,
mm-hmm.
he had nothing but just absolutely glowing things to say. And, this guy changed his life. He changed my grandpa's life. He changed, well, obviously the lives of all the babies he saved, but, all the people he worked with, all the people he, like also Dr. Avery, who he taught how to do some of these calculations. He changed her life. So just a really fun story of collaboration and also mentorship. What does that mean for people? How do you get where you're going? Sometimes it's luck, and sometimes it's you surround yourself with people who inspire you to care and people who inspire you to be the best version of yourself that you can be.
Yeah. Yeah. No, I really loved this story when I heard you give your talk, which was where I first heard this story. I just loved how many different threads it brought together, because it really seems like one of those like big serendipity moments. And also I loved how much like positive mentorship there was and how optimistic it was for science and translational research. And it's really like a big success story. You know, I kind of feel like I need that sometimes to continue moving forward with my extremely basic research that I'm not sure when it'll ever have a clinical implication, but you know.
And a lot of basic research, the clinical implications may not be discovered till years later. That's why I sort of love that there was also a failure in this story.
Yeah.
That sometimes something you think doesn't work may work in the end. I think your research is amazing. You know, I mean, for those listeners who may or may not know, Jamie does pain research. And pain, as you know, is a very underappreciated and undertreated condition. At least for me in rheumatology, I see pain all the time. And when it's inflammatory pain related to rheumatoid arthritis or lupus or something that I can treat with prednisone or something else, I get excited because I know I can make that pain go away.
Yeah.
But when it's not inflammatory pain and instead it's central sensitization or something of that sort, I actually feel this like rock in the pit of my stomach that I might not be able to help my patient with this.
Yeah, no, I feel very like motivated in my research because of how little we know about how to treat a lot of pain conditions. And I expect that in my future career, because I'm planning to go into anesthesiology and then do a fellowship in pain medicine, that I'll probably work a lot with rheumatologists.
Absolutely. Hit me up when you discover the cure for fibromyalgia, please.
Oh my God. that'll be a difficult one.
Or osteoarthritis. I
think there'll probably need to be a lot more collaboration with that one, because I probably won't study the joints all that much. My focus is on the brain.
The brain is cool too. I can appreciate the brain.
Yeah, persevere through failure. Get yourself good mentors. Be like John Clements. We really appreciate wholesome, just really amazing scientists. So go out there and be like him and be like Sharon's grandpa.
Yeah, my grandpa was pretty cool. I think the thing about him that I would want to put out there into the listening audience is that he was like so ridiculously optimistic about everything all the time. Even though he was an orphan, even though he had polio and was partially paralyzed for his whole life, even though he lived through World War II and all that followed, he always saw the good in people, and he always thought there was something that he could do to help. And he did help in his own way. Every person who's big in science or in medicine or in math or physics or computer science, even the big people only contribute a small sliver to our, combined human knowledge pool and experience. We cannot be the person who does it all individually. It's this huge collaborative effort. So it was also really fun to see where my grandpa came from, because he was a research fellow. Now I'm a fellow.
Yeah.
And okay, to think that this part of his career, this surfactant thingy, was just like such a tiny component of what he ended up doing. Even in your 20s and 30s and 40s, you may not be doing the thing that people remember you for. You might be doing some tiny sliver of something that gets you to the next step, and then you can pivot and you can change what you're doing and you can grow in new ways. So I love that about this story too.
Yeah. Yeah, that's really fantastic. And I mean, I wish I had known your grandfather. He sounds like a great guy.
Most of his older years, he was just telling us how cool the oranges were. He just really liked oranges. So he'd come to our house with a different orange every single time and just be like, this is the best orange that has ever existed. And we'd be like, Grandpa, you said that about the last orange. And he'd be like, no, but this one's really the best.
I mean it this time, for real.
I mean it this time.
No, this one's the best. That's amazing. Sharon, thank you so much for being on the podcast. This was a really great conversation and just so wholesome. Do you have any social media you want to plug or papers that you want people to read?
Sure thing. So I don't really do the social media thing at all. But if you want to go read the original paper that my grandpa was a part of It is available online. It's called Composition of Surface Active Material Isolated from Beef Lung. And my grandpa's name is Marshall Klaus with a K.
Yes. That will also be linked in the episode description and available as a PDF on the podcast website at inplainenglishpod.org. So you can get it there. It'll be really easy and you should read it. Papers from the 1900s actually tend to be pretty easy to read as compared to papers today. So I recommend it. And you'll have some cool background for how this all came about after listening to this podcast.
I also recommend Dr. Avery's paper where she made the connection between surfactant and what was called hyaline membrane disease at the time, but now we call neonatal respiratory distress syndrome. That is called Surface Properties in Relation to Atelectasis and Hyaline Membrane Disease. That was published in 1959 by one Dr. Mary Ellen Avery.
Yeah, I will also link that one.
Yeah, it's a great story. I'd love to chat with anyone who loves to chat about it. It was also just really great. Like, as someone who works in adult medicine and doesn't know anything about peds and doesn't know anything really about lung physiology, it's really fun to go back to the roots of the science and how do we even know how things work, right?
Yeah. How do we... This is also a cool story of like how we do science and how we make discoveries and the complicated root of those discoveries from, physicists doing math because they're curious about something to actually improving survival for preterm infants. So this is awesome. If people do want to talk to you about this, do you want to share a way they can get in contact with you? Or they could also get in contact with the podcast and send us an email and I'll put you all in contact.
That sounds good to me.
Okay. Yeah. So send an email to inplainenglishpod@gmail.com if you want to hear more about this whole surfactant story and chat more with Sharon, and I'll put you all in contact.
I love talking about this, so no need to hold back.
Awesome. Well, thank you again.
Thanks, Jamie. Pleasure to be here. It's my first podcast, so I'm really excited.
That was great. And once again, we've been talking with Dr. Sharon Abada about her grandfather, Dr. Marshall Klaus's work on surfactant protein. You can find his paper, as well as more information about Mary Ellen Avery and John Clements, in the description of this podcast. Our logo is by the wonderful team at Biographics. That's Jessica Higginbotham, Tania Lintz, and Yolanda Campos. Our music is by Sam Brunwasser. You can find more of his work on SoundCloud at Visuals Now Beats. And finally, be sure to follow us on Twitter, Facebook, and Instagram at Plain English Sci so that you never miss an episode or exciting news and updates about In Plain English. Again, that's PlainEnglishSci. Thanks once again for listening, and come back next time for another episode of In Plain English.